This is question 2. Another trainee electrician has carried out a similar investigation using copper wire instead of steel wire, so they're using copper rather than steel. And they've got a little table of results, and these seem to go up nicely. Number 8 seems to go down, and then 10 goes up again. Explain which result is an anomaly. Well, I think it's 8, but if we had a little graph here, and we had 2, 4, 6, 8, 10, 12, and we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, something like that. 1, 2, 3, 4, 5, yeah. Then 2 would be 1. I'll do that in a different colour. 4 would be 2. 6 would be 3. 8, that seems to go down to 1. 10 is 5. So you can see there that the anomaly is 8. So the current for 8 wires. Why? Because it doesn't fit the pattern, or doesn't fit the line of best fit. Does not fit pattern. It does not fit the line of best fit. Explain how you deal with this anomaly. What would you do if you had that result? Well, the way to deal with anomalies really is just to do more and more repeats, and the effect of that anomaly will be reduced. So certainly the best thing to do is to repeat the results. And then calculate a mean. Quite often you can't really just discard, throw away the result, because it might be right. You need to repeat it. Another possible thing you could do with it is, if you had a line of best fit there, so draw a graph, line of best fit, then take the reading from the graph. That's another possibility. So plot a graph, read value from the line of best fit. Part C, use the table to estimate the current that will melt 12 copper wires. Well, if I did it from my graph, then what seems to happen? Then I would go up there, 12, and it would just go to this sort of next one. That's the sort of thing I can imagine in my mind there. And these appear to be half. Current appears to be half of the number of wires, doesn't it? For the all the normal results. So this is going to be 6.0. So 6.0, and you need a unit there, amps. A trainee electrician used the following equipment: a ruler, an ammeter, a voltmeter, tested 4 wires and recorded percentage error. Right, we know about percentage error, don't we? And they've got these percentage errors. And he's saying the ammeter has got the biggest effect on the accuracy of the results. Well, what we're going to have to do here is calculate the percentage error. What is the percentage error here? And we've got various clues. Well, we've got our percentage error equals the precision of the equipment then we times that by 100 and then we divide by the measurement, the value. What is the precision? Well, the ammeter is in increments of 0.1 amps. The answer that they give might not be the answer that you have from your experiment, because their ammeter has values across here and it's kind of like a dial, whereas your ammeter had a digital kind of reading like a multimeter. So the precision will be different if we've got an analog scale. Then you can either have it on the increment or halfway between the increment. So the precision here will be 0.05 amps, and the precision on your digital one, well, it can only be kind of one value or the next one, so that will be 0.1 on this scale. So it depends on, oh, yours was 0.01, wasn't it? On this scale it would be 0.01. That's, yes, you had 2 decimal places on yours. So I'm going to do it for the one that you had. So you had on your digital multimeters, the precision was 0.01 times by 100 and divided by your value, which is 0.2 there. So when you put that into the calculator, 0.01 times by 100 divided by 0.2, and that is 5. Is that right? 5%. The mark scheme for this this one is 0.05 times by 100 divided by 0.2. 0.05 times by 100 divided by 0.2 is 25. So if you use that analog one with the dial on, the error will be different. Either way, the answer is the same. So the biggest percentage error is the one that is the least accurate. So this is the measurement. So 0.5, 2.5 against this bigger one, 5%. So this is the measurement that has the largest effect on accuracy, because it's got the largest percentage error. So you can do percentage error, so you should really get that right. Part E, 2 other reasons why there's a difference between your steel wool wire and copper alloy wire. So why might there be a couple of differences here? Well, there might be different. Your wire was very thin, but the copper wire might be, might be slightly thicker, possibly, or even thinner. That would affect the resistance, and so would affect the results. So I would suggest the first point is the wires may have different diameters or different thicknesses. The mark scheme suggests that the wires might be different lengths. So you might have a little wire and a bigger wire. But actually the experiment you did, you were told to keep the length the same. So I'm not sure that's a really good answer. I'm going to put that in brackets. Wires may be different lengths. And also the mark scheme suggests the equipment was hot. I'm not quite sure why that would be. I would suggest another reason why there might be a difference between your results and the copper is because the copper might have different resistance or different conductivity. So I'm gonna stick that in. So copper will have a different resistance or conductivity as a suggested answer. And the last part F, we've got another similar question to the one in the other paper about costing and which is the best material for the fuse wire, on whether you think the other electrician is right. Use the costings and the electrician's results to support your answer. Well, in truth, it depends on what sort of circuit is needed. But we usually what do we know from the costings? Well, we've got steel wool is 620 for 5 kilograms. How much is that per 1 kilogram? So 620 divided by 5. So that's £1.24. £1.24 per kilogram for steel. And copper, we get a 1 kilogram there, so that's £3.60. So at the very least, we're going to start our answer off, well, copper wire is more expensive. Is more expensive than steel wire. And they're going to give us a mark here for manipulating the data. So copper wire is £3.60 per kilogram, whereas steel is, I'll put the calculation in, so 620 divided by 5 equals £1.24 per kilogram. So 2 marks there, just for really seeing the difference between the copper and the steel in terms of price. And that's what it said, use the costings. And the other bit of information, where we're going to get this from. So, and the other trainee electrician's results. Where are the other trainee electrician's results? Well, we need to go back a bit to this experiment here. So these currents are higher than your current, I believe, when you did your graph. So that was your graph. So your maximum current was just over 2, whereas the electrician's current got up to, well, for 6 wires, slightly higher 3, but they've got it up to 12 wires. So actually there's not that much difference. They've got a slightly higher current needed to melt the wire. So we're using these results. That's what we're doing to support your answer. So is steel wool wire the best? Well, I reckon that steel is the best because it costs less and the results are actually not that different. They both, for your 6 wires it was about 2 amps, for their 6 wires it's about 3 amps. There's not that much difference. So I'm going to say there's not much difference in the steel versus copper results. And I'm going to give an example here, e.g. 6 wires steel was around 2 amps, copper is 3 amps. So best to use steel as similar currents needed to melt the wire, but it is much cheaper. Why would you buy something more expensive if it gives the same results? So we've got 4 marks there, but really it will depend on what sort of circuit you need, but will depend on what circuit is needed. So if they need slightly higher current, then they could get away with using less copper. It's easier to use as well as copper, but that's not actually it's not actually asking for that. So question 2, 14 marks.